There's a hidden network threading through the cosmos, an intricate web of invisible roads that stretch farther than our minds can fathom. Picture this, a vast, uncharted highway system where galaxies aren't just scattered randomly, but are connected by rivers of dark matter, gravitational currents, and cosmic filaments so immense they defy comprehension. This isn't science fiction, it's the cutting edge of discovery, a field known as cosmic cartography. Think of it as the ultimate map-making adventure, where scientists don't chart mountains or oceans, but the very scaffolding of the universe itself. And what they've found so far is nothing short of breathtaking. For centuries, humans have mapped every corner of our planet, from the deepest trenches to the highest peaks. But now we're turning our gaze outward toward the grandest frontier of all the cosmos. Out there, beyond the glow of familiar stars, lies a labyrinth of pathways woven into the fabric of space-time. Some are highways where galaxies glide effortlessly, pulled by the unseen hand of dark matter. Others are ancient, crumbling routes left behind by collisions of cosmic titans billions of years ago. These are the uncharted territories that cosmic cartographers are racing to decode, and what they're uncovering could rewrite everything we know about how the universe works. So why does this matter to you? Because hidden within these cosmic maps are answers to questions that have haunted humanity for millennia. How did the universe take shape? What forces hold it together, or might one day tear it apart? And perhaps most thrilling of all, are we alone in this vast expanse? This video is your ticket to the front lines of that exploration. We'll journey alongside the scientists who are peeling back the layers of the cosmos, revealing secrets that challenge our understanding of reality itself. From the faint whispers of gravitational waves to the ghostly trails of dark matter, every discovery is a piece of a puzzle so enormous, it spans the entire universe. Buckle up, we're about to embark on the greatest road trip imaginable, and the destination is nothing less than the farthest reaches of existence. The urge to map the heavens is as old as civilization itself. Ancient astronomers etched star patterns onto clay tablets and painted constellations across temple ceilings, using the night sky as both a celestial clock and a canvas for mythology. But what began as simple dots connecting imagined shapes has exploded into one of the most ambitious scientific endeavors in history. Modern cosmic cartography doesn't just plot stars, it reconstructs the universe in 3 dimensions, revealing structures so vast they make our Milky Way seem like a speck of dust. This revolution started with humble tools. In the early 20th century, Edwin Hubble peered through the lens of the Hooker telescope and made a staggering realization: those fuzzy nebulae weren't clouds within our galaxy, but entire galaxies themselves, racing away from us in every direction. His measurements of their redshifts became the first signposts on humanity's cosmic roadmap. Fast forward to today, and our instruments have grown exponentially more powerful. Projects like the Sloan Digital Sky Survey have scanned millions of galaxies, while the James Webb Space Telescope peers back to the dawn of time, capturing light from infant galaxies born just after the Big Bang. Yet the most astonishing breakthroughs come from what we can't even see. Dark matter, the invisible glue holding galaxies together, weaves through space in colossal filaments, forming a hidden skeleton beneath the visible universe. By tracking how galaxies move and cluster, scientists trace these unseen structures, much like mapping ocean currents by watching drifting boats. Supercomputers then transform terabytes of data into breathtaking simulations, revealing a universe laced with glowing tendrils of matter stretching across billions of light years. This isn't just about creating pretty pictures. Every new map forces us to rethink cosmic history. Some filaments appear too large to exist under current theories, hinting at gaps in our understanding of gravity or the universe's expansion. Others show eerie voids, regions nearly empty of galaxies, where the rules of physics might play out differently. And tucked within these models are clues to the universe's ultimate fate. Will it keep expanding forever or collapse back in a cosmic reversal? The answers are written in the stars. We're just learning how to read them. Dark matter is the universe's greatest unsolved riddle, an invisible architect shaping everything we see, yet slipping through our detectors like a ghost. Imagine building a house and only ever seeing the furniture inside, never the beams holding up the walls. That's the challenge scientists face when mapping dark matter. It doesn't emit, reflect, or absorb light, yet its gravitational pull is so powerful it bends the very fabric of space-time. So how do you chart something that's fundamentally undetectable? The answer lies in a cosmic trick of the light called gravitational lensing. Here's how it works. When light from a distant galaxy travels toward us, it doesn't move in a straight line if dark matter stands in its way. Instead, the light bends around these invisible masses, like a car swerving around an unseen obstacle. By studying these distortions, subtle warps in the shapes of background galaxies, researchers can reconstruct the hidden landscape of dark matter. The results are staggering. Maps created this way show dark matter isn't just floating aimlessly. It forms an intricate lattice, a cosmic spiderweb with galaxies clinging to its threads like dewdrops. The scale of these structures defies imagination. Some filaments stretch hundreds of millions of light years, weaving through the universe like the roots of a colossal tree. And just as roots nourish a forest, these dark matter highways dictate where galaxies grow. Dense knots in the web become galaxy clusters, while emptier regions, cosmic deserts, remain eerily vacant. But the real surprise, the web isn't static. Simulations reveal its dynamic, with galaxies surfing along dark matter currents over billions of years, pulled toward massive intersections in a slow-motion dance. This hidden framework also holds clues to one of physics' biggest mysteries. What is dark matter? Some theories suggest it's made of undiscovered particles, while others propose modifications to gravity itself. Each new map narrows the possibilities. For instance, when dark matter's distribution matches predictions based on gravity alone, it supports the particle theory. But when filaments appear thicker or more tangled than expected, it hints at gaps in our understanding. Perhaps most astonishing is how these maps rewrite cosmic history. By analyzing the web's structure, scientists can trace its evolution back nearly 14 billion years, revealing how tiny fluctuations after the Big Bang snowballed into the universe, spanning networks we see today. It's like uncovering fossilized footprints of the cosmos's infancy. And just as footprints tell us about the creature that made them, dark matter's fingerprints reveal secrets about the universe's birth, growth, and ultimate destiny. So next time you gaze at the night sky, remember, the stars and galaxies are just the visible frosting on an unimaginably vast cake. Behind them, shaping their every move, lies the invisible hand of dark matter, the silent cartographer of the cosmos. Gravity has built the universe's most spectacular roads, and they're nothing like the winding highways we know on Earth. These are the cosmic filaments, colossal threads of dark matter and ionized gas, some stretching over 500 million light years, that form the backbone of the cosmic web. Picture them as interstellar freeways, but instead of cars, they guide entire galaxies in a slow-motion migration that lasts billions of years. This isn't chaos, it's a meticulously organized traffic system written in the language of gravity. The cosmic web structure is so vast, it took supercomputers to reveal its true scale. Projects like the Millennium run a groundbreaking simulation that modeled the universe's growth, show galaxies aren't just floating adrift. They're drawn like magnets toward dense intersections where filaments meet, creating bustling hubs known as galaxy clusters. Meanwhile, the spaces between these filaments, they're cosmic ghost towns, voids so empty that if our Milky Way were stranded in one, our night sky would be nearly black. What's astonishing is how these superhighways shape galactic destiny. Galaxies cruising along filaments grow fat on the gas and dust swirling around them, birthing new stars at a furious pace. But once they reach a cluster, it's like hitting a gravitational metropolis. Collisions strip away their gas, turning vibrant spiral galaxies into dormant, elliptical relics. These clusters, glowing with superheated plasma, become the universe's graveyards for galactic youth. Yet the cosmic web isn't just a relic of the past, it's still under construction. Astronomers have spotted protofilaments, faint tendrils of gas in the early universe, which eventually grew into the highways we see today. Some filaments even glow with the faint light of hydrogen, lit up by quasars like cosmic street lamps. And here's the twist: the web structure holds fingerprints from the Big Bang itself. Tiny quantum fluctuations in the newborn universe stretched into these vast filaments, meaning the universe's largest structures were seeded by its smallest beginnings. So why does this matter? Because the cosmic web is more than a map, it's a time machine. By tracing its wrinkles, scientists can test theories about dark energy's push and dark matter's pull. Some filaments seem too thin, others too tangled, hinting at physics we've yet to grasp. And if we ever hope to understand where the universe is headed, we'll need to decode the highways it's built to get there. The cosmic web isn't just the universe's skeleton, it's the blueprint for everything. Somewhere in the depths of space, an invisible force tugs at our galaxy with the pull of a million suns. The Milky Way isn't drifting aimlessly, it's racing toward something colossal, something shrouded in mystery. Astronomers call it the Great Attractor, a gravitational anomaly so powerful it's dragging entire galaxy clusters toward it at speeds exceeding 1 million miles per hour. But here's the catch: we can't even see it directly. This cosmic heavyweight hides behind the Milky Way's dusty belly, a region so dense with stars and gas it's known as the zone of avoidance, because for decades it literally avoided our telescopes. The Great Attractor wasn't discovered by spotting it, but by noticing something far stranger. Galaxies weren't just expanding outward from the Big Bang as expected. Instead, a vast swath of them, including our own, were veering off course as if caught in a celestial riptide. In the 1970s, astronomers mapping cosmic motions first noticed this deviation, and the implications were staggering. Something out there, something with the mass of tens of thousands of Milky Ways, was bending the paths of galaxies like a magnet tugging at iron filings. So what could exert such unimaginable pull? Early theories ranged from a supermassive black hole to exotic dark energy phenomena. But as technology pierced through the zone of avoidance, a clearer picture emerged. The Great Attractor appears to be a sprawling supercluster of galaxies, anchored by a dense knot called the Norma cluster. Imagine a bustling galactic metropolis, its gravity so concentrated it warps the fabric of space-time around it. Yet even this explanation feels incomplete. The observed pull suggests there's more mass here than visible galaxies can account for, hinting at hidden reservoirs of dark matter or even larger structures beyond our current maps. The intrigue deepens when you consider scale. The Great Attractor isn't just a local curiosity, it's part of an even grander cascade. recent studies reveal our motion toward it is just the first leg of a longer journey. Beyond it lies the Shapley supercluster, a gargantuan assembly of matter that might be the true apex of this cosmic watershed. It's as if we're caught in a river flowing toward a waterfall, with the Great Attractor as merely a whirlpool along the way. Mapping this invisible force has required ingenuity. Astronomers have turned to X-ray telescopes to peer through the Milky Way's dust, revealing hot gas clouds swirling around the attractor's core. Radio telescopes have traced the motions of hydrogen gas, while infrared surveys have pieced together hidden galaxies. Each new dataset adds another stroke to the portrait, yet the full picture remains tantalizingly out of reach. The Great Attractor challenges more than just our instruments. It tests the limits of cosmic cartography itself. If such a massive structure could stay hidden in plain sight for so long, what else might lurk in the uncharted territories of the universe? Every answer unearths new questions, and in that tension lies the thrill of exploration. The cosmos doesn't give up its secrets easily, but that's what makes the hunt so exhilarating. The cosmic web isn't just a skeleton of dark matter. It's also pulsing with rivers of superheated gas, flowing between galaxies like an invisible interstate system. These intergalactic highways, detected as faint X-ray glows stretching across millions of light-years, are the universe's hidden fuel lines, pumping raw material into star-forming regions and shaping galactic evolution. Imagine a network of pipelines, but instead of water or oil, they carry ionized gas hotter than the sun's core, weaving through the voids like threads of fire. At the heart of this discovery is something called the warm-hot intergalactic medium, or WIM, a ghostly veil of gas so diffuse it's nearly transparent, yet so vast it may contain half the universe's normal matter. For decades, this stuff evaded detection, slipping through the cracks of our instruments like fog through a net. But X-ray telescopes like Chandra and XMM Newton finally caught its fingerprints, telltale spikes in radiation where the gas absorbs light from distant quasars, like spotting a highway at night by the glow of distant headlights. Mapping these gaseous rivers is like trying to trace the outline of a cloud with your fingertip. The WIM isn't just faint, it's dynamic, shifting as galaxies move and collide, redistributing matter across the cosmos. Some filaments funnel gas into galactic hubs, feeding supermassive black holes and sparking bursts of star birth. Others act as cosmic recycling plants, where supernova explosions blast heavy elements back into the web, seeding future generations of stars and planets. The implications are staggering. Without these gas highways, galaxies would starve, their star factories shutting down as fuel runs dry. But the WIM does more than just sustain, it connects. By tracing its tendrils, scientists have uncovered a hidden link between isolated galaxies, proving they're not solitary islands but nodes in a grand, interconnected system. Even more mind-bending, some of this gas is primordial, untouched since the Big Bang, offering a direct window into the universe's raw ingredients before stars or galaxies even existed. Yet for all its importance, the WIM remains full of puzzles. Why does some gas clump into dense knots while other regions stretch into wispy strands? How does it interact with dark matter's gravitational pull? Each answer peels back another layer of the cosmic web's complexity, revealing a universe far more dynamic and intertwined than we ever imagined. So the next time you hear about dark matter's cosmic scaffolding, remember, it's not just an empty framework, it's alive with currents of glowing gas, the lifeblood of the universe itself. Between the glowing highways of the cosmic web, there exists a different kind of wonder, vast, silent expanses where galaxies are so few and far between, you could travel for millions of years without encountering a single one. These are the cosmic voids, the universe's great emptiness, each one a bubble of near-nothingness stretching wider than our minds can comfortably grasp. Picture standing in the middle of an endless desert, where the horizon stretches unbroken in every direction, and you might begin to understand the sheer scale of these regions. But unlike any desert on Earth, these voids aren't just empty, they're alive with hidden forces shaping the very fate of the cosmos. The discovery of these voids rewrote our understanding of cosmic structure. For decades, astronomers assumed matter was spread somewhat evenly across the universe. But as maps of the cosmic web grew more detailed, a startling pattern emerged. Galaxies weren't just clustered along filaments. They were also avoiding enormous blank spots, as if repelled by some unseen force. The largest of these voids, like the Boötes void, span over 300 million light-years and contain only a handful of galaxies. If our Milky Way were adrift in one of these regions, our night sky would be almost pitch black, with neighboring galaxies too distant to see with the naked eye. Yet calling these voids empty is a cosmic misdirection. Within them drifts a sparse mist of hydrogen gas, so thin it's barely detectable, along with the occasional lonely galaxy, often misshapen and starved of the raw materials needed to form new stars. More intriguingly, these voids are flooded with dark energy, the mysterious force accelerating the universe's expansion. Without the gravitational pull of dense matter to counteract it, dark energy dominates here, stretching space itself apart faster than anywhere else in the cosmos. In a way, voids are like laboratories for studying dark energy's effects, a place where its influence is laid bare, unobscured by the clutter of galaxies. Mapping these voids has required ingenious techniques. Since so little inside them emits light, astronomers rely on indirect methods, like observing how light from distant quasars dims as it passes through void regions, or measuring subtle temperature variations in the cosmic microwave background. Each new observation reveals voids aren't static, they grow over time, their edges eroding as filaments funnel matter away, leaving behind even greater emptiness. Some voids even appear to be linked, forming a honeycomb-like structure that hints at an underlying order to the cosmos's apparent chaos. What's most surprising is how these voids shape the universe around them. Like the hollows in a block of Swiss cheese, their presence alters how galaxies move. The Milky Way, for instance, isn't just being pulled toward the Great Attractor, it's also being pushed by the repulsive effect of nearby voids, as if space itself is sliding downhill away from these empty regions. This push and pull dynamic means voids aren't just passive gaps, they're active players in the cosmic ballet, their gravitational absence sculpting the paths of galaxies as surely as dark matter's pull. Perhaps the greatest mystery lies in how voids formed in the first place. Current theories suggest they're the inverse of filaments, regions where matter was slightly sparser in the early universe, and over billions of years, gravity drained them further, like water flowing out of a bathtub. But some voids are so large and so empty that they challenge even our best simulations, leaving scientists to wonder if unknown forces or primordial fluctuations played a role. Peering into these abysses forces us to confront profound questions. Is the universe's accelerating expansion destined to turn everything into a void given enough time? Could life exist in one of those isolated void galaxies, looking out into a starless sky? And what other secrets might these cosmic deserts hold, hidden in their quiet depths? The answers, like the voids themselves, are vast, elusive, and waiting to be uncovered. Black holes have long been painted as the universe's ultimate villains, cosmic vacuum cleaners, sucking in everything that strays too close. But what if we've been telling only half the story? These gravitational monsters, especially the supermassive ones anchoring galaxies, might actually be the universe's guiding lights. Picture a lighthouse on a stormy coast, its beam cutting through the fog to reveal hidden channels. That's precisely what black holes do on a galactic scale, their fierce energy output acting as beacons that illuminate the darkest corners of the cosmos. Take the jets erupting from active black holes, colossal streams of particles shot outward at nearly the speed of light, stretching for thousands of light years. These aren't just spectacular light shows, they're cosmic probes. As these jets slam into surrounding gas, they heat it to millions of degrees, causing it to glow in X-rays. Astronomers use these emissions like breadcrumbs, tracing the otherwise invisible highways of intergalactic matter. It's as if black holes are spraying fluorescent paint across the cosmic web, revealing filaments and knots we'd never see otherwise. But their role goes even deeper. Some theories suggest supermassive black holes might be the unseen architects of galactic motion. Imagine a marble rolling along a groove. That's how galaxies glide along dark matter filaments. Now picture tiny bumps in that groove, subtly altering the marble's path. Black holes could be those bumps. Their immense gravity might nudge entire galaxies, steering them toward dense intersections in the cosmic web where clusters form. Simulations show that without black holes' influence, galaxies might not pile up so dramatically in these hubs, leaving the universe far more evenly scattered. The most fascinating clue comes from quasars, the blazing cores of distant galaxies powered by voracious black holes. These cosmic searchlights are so bright they outshine their host galaxies, visible across billions of light years. By mapping their positions, scientists have uncovered vast structures, like the Sloan Great Wall, a filament of galaxies over 1 billion light-years long. Quasars mark the densest junctions in this scaffold, hinting that black holes don't just inhabit the cosmic web, they might help build it, yet mysteries remain. Why do some black holes fire jets while others lie quiet? How exactly do they sync up with dark matter's pull? Each observation peels back another layer, revealing black holes not as destroyers, but as navigators, celestial cartographers etching the universe's grand design in light and gravity. So next time you hear about a black hole's appetite, remember, it might also be holding a pen, helping to draw the map of everything. Galaxies aren't frozen in place, they're cosmic commuters, riding the gravitational currents of the universe in journeys that last billions of years. Imagine the Milky Way not as an isolated island of stars, but as a passenger aboard one of these invisible superhighways, gliding toward destinations shaped by forces we're just beginning to understand. This grand migration isn't random. It's orchestrated by the pull of dark matter filaments, those colossal threads weaving through space like rivers, guiding galaxies toward dense intersections where clusters form. The Milky Way's own journey reveals how dramatic these voyages can be. Right now, we're hurtling toward the Andromeda Galaxy at 250,000 miles per hour, drawn together by mutual gravity in a slow-motion collision set to unfold over the next 4 billion years. But that's just one leg of a far longer trip. Our entire local group of galaxies is caught in the flow of the Laniakea supercluster, an immense structure 500 million light-years wide, whose gravity tugs us toward the Great Attractor like leaves floating down a cosmic stream. These motions aren't merely directional, they're transformative. When galaxies merge or pass near clusters, the gravitational tides can strip away their gas, quenching star formation and altering their structure forever. Yet some galaxies thrive on the move. Spiral galaxies like our own often flourish along filaments, where they gorge on fresh gas funneled by these cosmic channels, sparking bursts of new stars. But the moment they reach a dense cluster, the rules change. The surrounding hot plasma, a superheated fog between galaxies, acts like a sandblaster, stripping away their gas reserves and leaving them red and dead. their star-forming fuel exhausted. This explains why clusters are graveyards of aging elliptical galaxies, while the filaments between them teem with vibrant spirals still rich with young stars. Tracking these migrations has required ingenious detective work. Astronomers measure galactic motions using redshift, the stretching of light as galaxies move away from us, but also by studying the cosmic microwave background, the afterglow of the Big Bang. Subtle temperature variations in this ancient light reveal how galaxies are tugging at the fabric of space-time, allowing scientists to reconstruct their paths like tire tracks in cosmic snow. The resulting maps show galaxies don't just drift, they're channeled along predictable routes, converging where filaments intersect in a celestial version of rush hour traffic. These movements aren't just about where galaxies are going, but where they've been. By rewinding their motions, scientists have uncovered a shocking truth. Many of today's majestic spirals were built from violent collisions, their stars and gas reshuffled like cosmic puzzle pieces over eons. Even more startling, some galaxies are interlopers, strangers flung into clusters from distant voids, their unusual orbits betraying origins far from their current homes. So where is it all leading? Simulations suggest the universe's largest structures will keep growing, with filaments funneling galaxies into ever greater clusters until dark energy stretches the cosmic web too thin for new migrations to begin. For now, though, the highways are open, and galaxies like ours are still traveling, each one a testament to the unseen forces writing the universe's grand story in motion. The universe's baby picture hangs in the void, a faint, crackling glow that's been traveling toward us for nearly 14 billion years. This is the cosmic microwave background, or CMB, the oldest light in existence, released when the universe cooled enough for atoms to form and photons to finally travel freely. But it's far more than a relic. It's a treasure map encoding the blueprint for everything that followed. Within its subtle temperature variations, hot spots and cold spots differing by mere millionths of a degree, lie the seeds of the cosmic web, the gravitational footholds that would one day grow into galaxies, filaments, and voids. Capturing this map required instruments of unprecedented sensitivity. The Planck satellite, launched in 2009, spent 4 years scanning the entire sky, measuring the CMB's imperfections with a precision akin to spotting a grain of sand on the moon from Earth. What it revealed was astonishing, a patchwork of slightly denser regions where matter had begun to clump, driven by quantum fluctuations from the universe's first trillionth of a second. These tiny ripples, stretched to cosmic scales by the Big Bang's expansion, became the scaffolding for all structure, the hotter spots, future galaxy clusters. The cooler patches, the sprawling voids we see today. But how did these faint wrinkles evolve into the universe we recognize? Gravity did the heavy lifting. Over eons, denser regions pulled in surrounding matter, growing like snowballs rolling downhill. Dark matter, invisible yet omnipresent, formed an invisible skeleton, its gravity funneling gas into the valleys of its potential wells. Meanwhile, the emptier regions thinned further, drained by the growing filaments around them. Supercomputer simulations, like time-lapse videos of the cosmos, show this process in action. What begins as a nearly smooth primordial soup twists and knots into an intricate web, mirroring the CMB's fluctuations with eerie precision. The CMB doesn't just tell us where structures formed, it reveals why they formed. Certain patterns in its fluctuations hint at the universe's composition. Roughly 5% ordinary matter, 27% dark matter, and 68% dark energy. These ratios dictated how quickly filaments condensed and voids ballooned. For instance, if dark matter had been more sluggish, galaxies might have taken longer to assemble, leaving the cosmic web threadbare. If dark energy had dominated earlier, the web might have been torn apart before it fully formed. The CMB is the ultimate cosmic recipe, and we're just learning to read its ingredients. Yet some mysteries persist. A few large-scale features in the CMB, like the cold spot, defy expectations. Could they be scars from collisions with other universes or flaws in our theories? Other anomalies suggest the cosmos might be lopsided, expanding faster in one direction than another. Each question sends scientists back to the drawing board, refining models and designing new missions to probe deeper. Future telescopes, like the proposed Lightbird satellite, aim to study the CMB's polarization, a faint twisting of light that could reveal gravitational waves from the Big Bang itself, offering clues about the universe's violent birth. What's truly humbling is realizing that every galaxy, every filament, every void we map today was written into the cosmos before stars even existed. The CMB is more than a snapshot. It's a prophecy, a whisper from the dawn of time that still guides our exploration. So when cosmologists trace the tendrils of the cosmic web, they're not just mapping space, they're reading a story that began before atoms, before light, before time as we know it. And the next chapters are waiting to be decoded. We're standing on the brink of a cosmic revolution, a leap in mapping the universe so profound. It's like swapping a candle for a floodlight. The next generation of sky surveys, armed with cutting-edge technology, is about to peel back the veil on the cosmic web with unprecedented clarity. Leading this charge is the Euclid Space Telescope, a European Space Agency mission designed to scrutinize the dark universe with the precision of a cosmic detective. Unlike traditional telescopes that focus on visible light, Euclid's infrared eyes will peer through dust and gas, capturing the faint glow of billions of galaxies across 10 billion years of cosmic history. But here's the real game changer. Euclid won't just photograph these galaxies, it will measure their distortions, revealing how dark matter bends their light in a technique called weak gravitational lensing. This data will produce the most detailed 3D map of dark matter ever created, exposing filaments and voids with startling clarity. Meanwhile, on the ground in Chile, the Vera Sea, Rubin Observatory is preparing for an equally monumental task. Its 8.4-meter mirror and massive 3,000-megapixel camera will scan the entire southern sky every few nights, a project so vast it's been dubbed the Legacy Survey of Space and Time. Over a decade, Rubin will detect tens of billions of galaxies, tracking their motions with such precision that scientists can reconstruct the gravitational tides of the cosmic web in real time. Imagine watching a time lapse of the universe's highways, with galaxies flowing like cars on a freeway, their paths dictated by the invisible hand of dark matter. Together, these missions tackle one of cosmology's biggest puzzles: dark energy's role in shaping the cosmic web. Is it a constant force, or does its strength change over time? Euclid's galaxy maps will measure the universe's expansion rate across epochs, while Rubin's supernova observations will serve as cosmic mile markers, testing whether dark energy's push is accelerating. The answers could rewrite our understanding of the universe's fate. Will it end in a cold, empty fade or a dramatic collapse? But the surprises don't stop there. These surveys might uncover anomalies in the cosmic web's structure, filaments that defy gravity's predictions or voids that seem too empty to exist. Such quirks could hint at entirely new physics, like exotic dark matter particles or modifications to Einstein's theory of relativity. There's even a chance they'll spot primordial black holes, ancient relics from the Big Bang that could be hiding in dark matter's shadowy folds. What makes this era unique isn't just the scale of data, but how it connects the dots across cosmic history. By comparing Euclid's deep space maps with Rubin's time-lapse of nearby galaxies, scientists can trace how the web evolved, from its faint beginnings in the CMB to the sprawling metropolis we see today. It's like assembling a billion-piece puzzle where every galaxy is a clue, and the picture emerging is nothing short of the universe's autobiography. The stakes couldn't be higher. If the cosmic web is the universe's circulatory system, these missions are its MRI scan, revealing not just its structure but its vital signs. And just as medical imaging transforms diagnoses, this new cosmic cartography could diagnose the health of our universe, whether it's expanding forever, destined to rip apart, or cycling toward rebirth. The highways of the cosmos are about to get their most thorough traffic report yet, and the detours might lead us straight to the frontiers of physics. The universe is too vast, too intricate for human eyes alone to map its hidden highways, but we've found an extraordinary ally in the quest. Artificial intelligence has become the silent partner of cosmic cartographers, crunching numbers and spotting patterns in datasets so enormous they'd take a human lifetime to parse. Imagine sifting through a beach grain by grain, searching for a single speck of gold. That's what it's like hunting for cosmic filaments in petabytes of telescope data. AI doesn't just speed up the search, it sees connections we'd miss entirely, revealing the universe's scaffolding in ways that defy traditional astronomy. Take galaxy classification, for example. For decades, astronomers painstakingly sorted galaxies into spirals, ellipticals, or irregulars by eye, a process as tedious as it was essential. Now, machine learning models like those used in the Galaxy Zoo project analyze millions of galaxy images in hours, spotting subtle features, a warp in a spiral arm, the faint glow of a merging companion, that hint at a galaxy's history and trajectory through the cosmic web. These algorithms don't just mimic human judgment, they surpass it, identifying rare, rogue galaxies ejected from clusters or spotting nascent filaments forming between galactic neighbors. But AI's real power lies in prediction. By training on vast simulations like the Millennium Run, neural networks can infer the presence of dark matter filaments where telescopes see nothing at all. It's akin to predicting underground rivers by watching how trees cluster on a landscape. In one groundbreaking study, an AI analyzed the motions of thousands of galaxies and reconstructed the cosmic web with startling accuracy, unveiling tendrils of dark matter that had eluded detection for years. Other models simulate cosmic evolution at breakneck speed, testing how slight tweaks to dark energy's strength or dark matter's properties would reshape the universe over billions of years. Experiments that would take supercomputers centuries to run unaided. The next frontier, real-time cosmic cartography. Projects like the Square Kilometre Array, a radio telescope network spanning continents, will flood servers with exabytes of data daily. AI will be the only tool capable of processing this deluge, flagging anomalies, perhaps a filament bending oddly, suggesting unseen mass, or spotting ultrafast changes, like galaxies abruptly altering course as they encounter dark matter currents. There's even talk of AI-designed telescopes, with machine learning optimizing mirror shapes or observation schedules to probe the cosmic web's faintest edges. Yet for all its prowess, AI isn't replacing astronomers, it's amplifying them. Like a microscope revealing cells for the first time, these tools expose hidden layers of cosmic structure, letting scientists ask questions they couldn't even frame before. What happens when two filaments collide? Do voids have substructure? Each answer peels back another layer of the universe's grand design, proving that sometimes to map the infinite, you need a mind that isn't human at all. Dark energy is the universe's greatest enigma, an invisible force not just expanding space but doing so at an ever-increasing speed, as if the cosmos itself is pressing down on the accelerator. Unlike gravity, which pulls matter together, dark energy pushes it apart, stretching the cosmic web like taffy over billions of years. This relentless push doesn't just move galaxies, it reshapes the very highways they travel, altering the map of the universe in ways we're only beginning to grasp. The discovery of dark energy was a cosmic curveball. In the late 1990s, astronomers studying distant supernova made a startling realization. These exploding stars were dimmer than expected, meaning they were farther away than their redshift suggested. The universe wasn't just expanding, it was accelerating, as if some unseen repulsive force was overpowering gravity's pull. This revelation turned cosmology on its head, forcing scientists to confront a baffling truth. 70% of the universe's energy budget is something we can't see, touch, or even fully explain. Now, cosmic cartographers face a daunting challenge. Dark energy doesn't just add distance between galaxies, it stretches the filaments of the cosmic web, thinning them like strands of spider silk in a windstorm. Over time, this stretching could sever the delicate bridges between galaxy clusters, isolating them in expanding voids. Mapping these changes is like trying to chart a river while its currents shift beneath your feet. Yet within this chaos lies a clue. By measuring how dark energy warps the web's structure over cosmic time, scientists can test whether its strength has changed since the universe's infancy. The leading theory pins dark energy on the cosmological constant, a term Einstein once called his greatest blunder, representing the energy inherent to empty space itself. If this constant holds, dark energy's push will remain steady, and the cosmic web will slowly fray into disconnected islands. But some models suggest dark energy might evolve, growing stronger or weaker over time. Imagine a highway where the lanes widen unpredictably, forcing cars to adjust speed erratically. If dark energy behaves this way, it could trigger a big rip, tearing apart galaxies, stars, and even atoms in the far future. Cutting-edge surveys are hunting for answers by mapping the web's growth across billions of years. Projects like DAISY, the Dark Energy Spectroscopic Instrument, measure the precise positions of millions of galaxies, tracing how their clustering patterns stretch or compress as dark energy works its magic. Other experiments, like the upcoming Nancy Grace Roman Space Telescope, will peer back to when the universe was half its current age, searching for signs that dark energy's grip has tightened or loosened over time. The stakes couldn't be higher. If dark energy isn't constant, our entire understanding of gravity, and by extension, the universe's fate, may need rewriting. Some theorists even speculate that dark energy could be the footprint of extra dimensions, or a sign that Einstein's relativity breaks down on cosmic scales. Every new filament mapped, every void measured, brings us closer to solving this puzzle. The cosmic web isn't just a snapshot of the universe, it's a time-lapse of dark energy's invisible hand at work, and decoding its patterns might reveal where this grand journey ends. Science fiction has always been a playground for cosmic cartography, painting vivid pictures of how we might one day navigate the universe's uncharted depths. Take Star Trek's iconic star charts, those glowing holographic maps that let the Enterprise zip between star systems with pinpoint accuracy. While we're centuries away from such seamless interstellar travel, the idea isn't pure fantasy. Today's astronomers use 3D models of nearby stars, plotting their positions and motions with precision that would make even Starfleet proud. The difference. Instead of warp drives, we rely on telescopes like Gaia, which has mapped over 1 billion stars in our galactic neighborhood, revealing their movements across millennia. Then there's Interstellar's mind-bending Tesseract, a fifth-dimensional library where time becomes a physical dimension you can navigate like a bookshelf. It's a poetic metaphor for how gravity warps space-time, but here's where reality diverges. While Einstein's theories confirm that massive objects like black holes distort time, we've yet to find evidence of higher dimensions or portals through them. That said, the film's portrayal of Gargantua's accretion disk, a swirling halo of superheated gas, was so accurate, physicist Kip Thorne used it to publish a scientific paper on black hole visual effects. Sometimes fiction doesn't just imagine the cosmos, it helps us see it more clearly. Even the star maps from Dune, with their emphasis on spice-fueled navigation, echo a real challenge, traversing a universe where dark matter and energy reshape the paths between stars. Without something like the spice melange to bend space, our probes rely on gravity assist slingshotting around planets to gain speed, a far cry from the instantaneous jumps of sci-fi lore. Yet both grapple with the same truth: the cosmos isn't static. Just as sandworms alter Dune's deserts, cosmic forces constantly rewrite the universe's roadways. Where sci-fi often overshoots is in scale. Franchises like Star Wars depict galaxies as bustling cities, with planets just a short hyperspace hop apart. In reality, the average distance between stars in our Milky Way is 5 light-years, a gap so vast even light takes half a decade to cross it. But these exaggerated maps serve a purpose. They shrink the universe into something humans can emotionally grasp. After all, a story set in real cosmic distances would spend centuries in transit, not exactly blockbuster material. The most tantalizing overlap between fiction and reality. The idea of a galactic internet, a network linking civilizations across the stars. While we've found no alien Wi-Fi, projects like SETI scan radio waves for patterns, and the Breakthrough Starshot initiative aims to send microprobes to Alpha Centauri, carrying digital records of humanity. It's a far cry from Mass Effect's mass relays, but the dream is the same: to weave the cosmos into a connected whole. Perhaps the greatest gift of sci-fi's cosmic maps isn't their accuracy, but their ambition. They push us to think beyond telescopes and equations, to imagine a future where the universe isn't just observed, but truly explored. And as our real maps grow richer, with filaments of dark matter and rivers of ionized gas, they're becoming stranger and more wondrous than fiction ever dared to predict. Long before supercomputers or space telescopes, humans were already charting the cosmos with nothing but naked eyes and patient observation. The Babylonians etched star positions onto clay tablets over 3,000 years ago, tracking planetary motions with such precision their data still holds up today. Half a world away, the Maya built entire cities aligned to celestial events, their temples acting as stone calendars marking Venus's cycles and solar eclipses. What's astonishing isn't just their accuracy, it's how some of their celestial patterns eerily foreshadow discoveries we've only made in the last century. Take the Dendera zodiac, an Egyptian temple ceiling carving depicting constellations in positions that, when adjusted for Earth's wobble over millennia, match ancient sky maps we've reconstructed using modern astronomy software. These early astronomers didn't just record stars, they sensed deeper cosmic rhythms. Polynesian navigators memorized star paths to sail across the Pacific, using the flicker of certain stars to detect distant islands beyond the horizon. Their mental maps included star compasses, where the rising and setting points of key stars acted as celestial highways guiding voyages. Today, we recognize these same stars as part of the Milky Way's local arm, their apparent motions reflecting our solar system's journey through the galaxy. It's as if these navigators intuited galactic structure centuries before we had the math to prove it. The real shocker: some ancient sites encode cosmic scales we thought beyond pre-telescope vision.
At Chichén Itzá, the Mayan pyramid El Castillo casts a serpent-shaped shadow during equinoxes, but less known is how its 4 stairways mirror the Milky Way's quadrants in certain seasons. Meanwhile, in Cambodia, the temples of Angkor Wat align not just with solstice sunrises, but with the Draco constellation's position 13,000 years ago, a time frame matching Hindu cosmological cycles. Could these cultures have preserved astronomical knowledge across generations that hinted at the universe's vast age? Modern technology is now testing these connections. Archaeoastronomers use LiDAR scans and 3D modeling to analyze how ancient structures interact with celestial events, uncovering alignments too precise for coincidence. In one breakthrough, researchers found that Britain's Stonehenge isn't just a solar calendar, its inner, bluestone circle aligns with lunar standstill cycles that occur only every 18.6 years. Such findings suggest early sky watchers detected patterns in cosmic chaos, much like how we now map dark matter's influence through galactic motions. What fascinates scientists most are the anomalies cases where ancient records describe celestial phenomena we can't easily explain. The Maori of New Zealand spoke of Te Ikaroa, a long fish in the sky that modern researchers suspect might represent the Magellanic Clouds, satellite galaxies of the Milky Way visible only from the southern hemisphere. Even more puzzling, Babylonian tablets mention a red star near Jupiter that matches the position of Uranus, a planet supposedly invisible without telescopes. While these could be coincidences, they raise tantalizing questions about lost methods of observation. The lesson for modern cosmic cartography: sometimes the oldest maps hold kernels of truth we're only now equipped to verify. Just as dark matter filaments guide galaxies, ancient star myths might guide our research not as literal blueprints, but as whispers from generations who studied the sky with different tools and saw patterns we're still learning to decode. In a way, today's most advanced telescopes and AI models are continuing a tradition that began with stone circles and clay tablets, the human urge to find order in the stellar dark. Mapping the universe in 3 dimensions is like trying to reconstruct a city's skyline using only flickering candlelight glimpsed through fog. The sheer scale of cosmic distances alone would be daunting enough. After all, light from the Andromeda Galaxy takes 2.5 million years just to reach us. But the real challenge lies in deciphering depth from the flat, 2-dimensional snapshots our telescopes capture. Imagine looking at a photograph of a forest and trying to guess which trees are close together and which are miles apart based solely on their brightness. That's the puzzle astronomers face every time they peer into the night sky. Redshift, the stretching of light as galaxies move away from us, has long been the gold standard for measuring cosmic distances. The farther a galaxy is, the faster it recedes due to the universe's expansion, and the more its light shifts toward the red end of the spectrum. It's a brilliant tool, but it's not foolproof. Dust clouds between galaxies can scatter light, mimicking redshift effects. Some galaxies are also rogue travelers, moving against the cosmic flow due to local gravitational tugs, skewing distance calculations. And then there's the finger of God effect, where dense galaxy clusters appear elongated in redshift maps because their gravity warps space-time, like viewing a street lamp through a funhouse mirror. To untangle these distortions, scientists deploy a cosmic toolbox of cross-checking techniques. Standard candles celestial objects with known brightness, like Type Ia supernova, act as mile markers. By comparing a supernova's apparent brightness to its expected luminosity, astronomers can calculate its distance independently of redshift. Another trick involves baryon acoustic oscillations, faint ripples in the distribution of galaxies left over from sound waves in the early universe.
These ripples have a predictable scale, letting researchers use them as a cosmic ruler. It's like recognizing the consistent spacing between telephone poles along a highway to judge how far you've traveled. Even with these tools, gaps remain. The universe's expansion isn't perfectly uniform, and dark energy's influence adds another layer of complexity. To fill in the blanks, astronomers turn to photometric redshift, a method that estimates distances by analyzing a galaxy's color across multiple wavelengths. While less precise than spectroscopic redshift, it's far quicker, allowing surveys like the Dark Energy Survey to map hundreds of millions of galaxies in a fraction of the time. Supercomputers then stitch these measurements into 3D models, simulating the cosmic web structure with algorithms that account for gravitational lensing, galaxy motions, and even the universe's curvature. The result, a map that's still incomplete but breathtaking in its ambition. Some regions, like the zone of avoidance hidden behind our Milky Way's dusty disk, remain stubbornly blank. Others are plagued by cosmic variance, a statistical noise caused by the universe's large-scale structure appearing different in one patch of sky versus another. Yet with each technological leap, from space telescopes piercing through dust to AI untangling measurement errors, the fog lifts a little more. The ultimate goal isn't just a static snapshot, but a dynamic atlas showing how the cosmic web evolves over billions of years, a project as much about time as it is about space. And every uncertainty resolved brings us closer to answering the biggest question of all: what this vast, tangled highway system tells us about where the universe came from and where it's headed. What if the cosmic web isn't just the scaffolding of our universe, but a borderland between countless others? The idea might sound like science fiction, but some of the most cutting-edge theories in physics suggest that the filaments and voids we've been mapping could be cosmic fingerprints of a multiverse. Imagine standing at the edge of a vast forest, unaware that what seems like the horizon is actually the threshold to another woodland entirely. That's the tantalizing possibility hanging over modern cosmology. Our universe's sprawling highways might not just connect galaxies, they could brush up against entirely separate realities. The concept stems from inflationary theory, which describes how our universe expanded exponentially in the first fraction of a second after the Big Bang. Some versions of this theory propose that inflation didn't stop everywhere at once. Instead, it could have created bubble universes, each with its own laws of physics, sprouting endlessly like froth in an ocean. Where these bubbles meet, their boundaries might leave imprints on the cosmic web, warping filaments or creating unnatural voids. It's a bit like finding seams in a patchwork quilt, subtle lines hinting at where one fabric ends and another begins. Not all evidence is purely theoretical. Astronomers have spotted peculiar anomalies in the cosmic web regions where filaments seem to abruptly terminate or voids appear too empty, as if something beyond our universe is tugging at the fabric of space. One controversial study even pointed to a so-called cold spot in the cosmic microwave background, a vast, inexplicably chilly region that some speculate could be a bruise from a collision with another universe. Of course, these observations are hotly debated. Skeptics argue they could simply be statistical flukes or artifacts of incomplete data. But for multiverse theorists, they're tantalizing breadcrumbs leading toward a radical redefinition of reality. The real challenge, testing these ideas without stepping outside the universe. Scientists are getting creative, though. Some are running ultra-precise simulations to predict how bubble universes might deform the cosmic web, then comparing those models to actual sky surveys. Others are hunting for gravitational wave patterns that could carry echoes of ancient collisions between universes. And if dark energy's strength varies across space, another multiverse hint future telescopes like the Nancy Grace Roman Space Telescope might detect its fingerprints in how voids expand. Even if the multiverse remains unproven, the pursuit reshapes how we see our own cosmic map. Those filaments we've been charting, they might not just be roads through space, they could be walls between worlds. And every anomaly, every unexplained void, becomes a potential window into something far stranger. The universe's highways may not just lead to distant galaxies, they could point to realities beyond our wildest imagination. The Hercules Corona Borealis Great Wall stretches across 10 billion light-years, a structure so immense it would take a beam of light, racing at the universe's speed limit, an unimaginable span of time just to traverse it. This isn't just a cluster of galaxies, it's a sprawling metropolis of matter, a cosmic continent dwarfing everything we once thought possible. Discovered in 2013 by mapping gamma-ray bursts the death cries of massive stars. This titanic formation defies a fundamental rule of cosmology. The universe should look roughly the same in all directions on the largest scales. Yet here it is, a thread of galaxies and dark matter so vast it seems to mock our models of cosmic evolution. Not to be outdone, the giant arc, a crescent of galaxies spanning 3.3 billion light-years, adds another wrinkle to the mystery. Found in 2021 by astronomers sifting through light from distant quasars, this structure isn't just big, it's perfectly curved, as if the universe itself drew a smile across the cosmos. The problem, according to our best theories, structures this size shouldn't have had enough time to form after the Big Bang. It's like finding a 1,000-year-old oak tree in a forest that's only been growing for a century. These megastructures aren't just curiosities, they're cosmic rebellions, challenging the cosmological principle that the universe is homogeneous at grand scales. Imagine stirring cream into coffee and finding, instead of a smooth blend, ribbons of cream weaving patterns larger than the cup itself. That's the enigma astronomers face. Some theorists suggest these formations could be scars from the universe's infancy, when quantum fluctuations were frozen into the fabric of space-time during inflation. Others whisper about exotic physics, dark energies' influence weakening in certain regions, or even gravitational echoes from a universe that existed before our own. Then there's the South Pole Wall, a curtain of galaxies hidden behind the Milky Way's glare, and the Sloan Great Wall, a filament of superclusters so long it could bridge the gap between Earth and the farthest quasar. Each discovery pushes the boundaries of what we thought the cosmos could build, forcing us to ask, are these structures rare jewels in the cosmic web, or are we just beginning to see the universe's true skeletal framework? The irony is delicious. The same telescopes built to confirm our theories are now tearing them apart. Every time we map deeper, we find another anomaly, another impossible structure grinning back at us from the dark. Whether these giants are rewriting cosmology or merely exposing gaps in our knowledge, one thing's certain: the universe's highways are far grander and far stranger than we ever dreamed. There's a cosmic messenger slipping through the universe unnoticed, a ghostly particle so elusive it can pass through entire planets without a single interaction. Neutrinos, nearly massless and electrically neutral, are the universe's stealth travelers, born in the hearts of exploding stars, colliding black holes, and other cataclysmic events. Unlike light, which can be absorbed or bent by dust and gravity, neutrinos barrel through space unimpeded, carrying secrets from the most violent corners of the cosmos straight to our detectors. This is neutrino astronomy, a revolutionary way to map the universe not by what we can see, but by what silently pierces through everything. At first glance, detecting neutrinos seems impossible. A single neutrino can sail through a light year of lead without hitting a single atom. Yet scientists have built traps for these phantoms, like the Ice Cube Neutrino Observatory, a colossal detector buried deep in the Antarctic ice. When a rare neutrino does collide with an atom, it creates a flash of blue light, a signal ice cube's sensors capture, tracing the particle's origin back to distant galaxies. It's like standing in a dark forest, listening for the faintest snap of a twig to pinpoint an invisible creature's location. What makes neutrinos so transformative for cosmic cartography is their ability to reveal hidden realms. Take active galactic nuclei, supermassive black holes devouring matter and spewing jets of energy. While telescopes see their glowing cores, neutrinos tell us about the particle accelerators near the event horizon, where protons smash together at energies far beyond anything we can recreate on Earth. In 2018, IceCube traced a high-energy neutrino to a blazar 4 billion light-years away, marking the first time we've pinpointed a cosmic ray source. It was like finding a cosmic postmark on a letter sent from the edge of a black hole. But neutrinos don't just complement light-based astronomy, they sometimes contradict it. In supernova, for instance, most of the energy isn't emitted as light but as neutrinos. When supernova 1987 exploded, detectors caught a burst of neutrinos hours before telescopes saw the flash, proving these particles escape collapsing stars faster than photons. This duality gives us a more complete picture. Light shows us the fireworks colors, while neutrinos reveal the fuse's spark. The real promise lies in mapping the universe's darkest corners. Neutrinos from the Sun's core have already confirmed nuclear fusion processes, but high-energy neutrinos could expose phenomena light can't reach, like the cores of neutron stars or the annihilation of dark matter. Future detectors, like the planned Pacific Ocean Neutrino Array, aim to catch even fainter signals, potentially uncovering sources we've never imagined. Neutrino astronomy is still in its infancy, but it's already clear. To chart the cosmos fully, we need more than eyes. We need to listen for the whispers of particles that travel unscathed through time and space, carrying stories from places no telescope will ever see. Every flash in the ice, every rare collision, is a new stitch in the tapestry of the universe, one woven not with light, but with ghosts. Hidden beneath the visible glow of galaxies and the dark matter scaffolding lies another cosmic architect: magnetism. These invisible fields weave through the universe's highways, so faint you could hold a refrigerator magnet next to them, and it would seem overpowering by comparison. Yet over vast distances and timescales, their influence adds up, guiding the flow of gas, shaping star formation, and even leaving fingerprints on the cosmic microwave background. Think of them as the universe's silent traffic controllers, subtly directing the movement of matter along filaments without ever flashing a visible signal. Detecting these fields isn't for the faint of heart. Unlike dark matter's gravitational tug or the glow of ionized gas, magnetic fields don't emit light or bend space-time in obvious ways. Instead, scientists rely on cosmic sleuthing tricks. One method studies polarized light waves that vibrate in a preferred direction, scattered by dust grains aligned with magnetic fields. It's like reading the grain of cosmic wood to infer the direction of an invisible current. Another technique tracks the spiraling paths of electrons moving through these fields, which emit a telltale radio signal called synchrotron radiation. These faint whispers, picked up by radio telescopes like the Very Large Array, reveal magnetic threads stretching between galaxies, often tracing the same filaments we've mapped in dark matter. But magnetism's real magic lies in how it shapes the universe's fuel supply. Gas flowing along cosmic filaments isn't just pulled by gravity, it's also channeled and braked by magnetic fields. In some regions, these fields act like cosmic baffles, slowing down turbulent gas and allowing it to cool enough to collapse into stars. Elsewhere, They might prevent gas from reaching galaxies at all, stranding it in the voids between filaments. Simulations show that without magnetism, galaxies might form stars too quickly, burning through their fuel before they've had time to grow. It's a delicate balance: too much magnetic resistance, and the universe's star factories stall; too little, and they overheat. The most tantalizing clues come from the universe's infancy. Tiny magnetic fields, amplified over billions of years by the motion of ionized gas, could explain why some filaments appear more tangled than gravity alone predicts. Some theorists even speculate that primordial magnetism, a relic from the Big Bang itself, might have seeded these fields, leaving a faint imprint in the cosmic web structure. If true, today's magnetic highways could be echoes of the universe's first moments, stretched to cosmic scales by expansion, yet mysteries abound. Why do some galaxy clusters host magnetic fields 1,000,000 times stronger than the filaments connecting them? Could magnetism explain why certain voids seem emptier than simulations predict? Each new observation peels back another layer, revealing a universe where invisible forces sculpt visible reality. So the next time you marvel at a galaxy's spiral arms, remember they're not just shaped by gravity's pull, but by the quiet, persistent hand of magnetism, writing its story across the cosmos. What if cosmic cartography could become a time machine, not just charting the universe as it is, but revealing how it was and how it will be? The idea isn't as far-fetched as it sounds. Every map of the cosmic web is already a snapshot of the past, since light from distant galaxies takes millions or billions of years to reach us. But scientists are pushing further, using supercomputers to simulate the universe's evolution backward and forward in time, like rewinding and fast-forwarding a cosmic film. These simulations don't just reconstruct history, they hint at something even more profound: the possibility that by decoding the universe's structure deeply enough, we might one day predict its ultimate fate. Take the cosmic microwave background, that ancient glow from the universe's infancy. Its subtle temperature variations aren't just a relic, they're the starting conditions for everything that followed. By feeding these patterns into simulations, researchers can rewind the universe's expansion, watching as galaxy clusters dissolve into filaments, filaments fray into primordial gas clouds, and everything funnels back toward the Big Bang's fiery dawn. It's like reconstructing a shattered vase from its fragments, piecing together each crack until the original shape emerges. But here's the twist: if we can simulate the past this accurately, could we also project forward, forecasting where the cosmic web is headed next? The answer hinges on dark energy, that mysterious force accelerating the universe's expansion. If its strength remains constant, the cosmic web will slowly stretch apart, filaments thinning until galaxies are isolated islands in an ever-growing void. But if dark energy evolves, becoming stronger or weaker over time, the web's fate could be far more dramatic. Some simulations suggest a big rip, where dark energy's grip grows so powerful it shreds galaxies, stars, and even atoms. Others hint at a cyclical universe where expansion eventually reverses, collapsing the web back into a singularity, the key to predicting which scenario awaits us. Mapping the cosmic web's growth with unprecedented precision, measuring how filaments and voids stretch or compress over billions of years. Yet even if we crack the code, philosophical questions loom. If we could rewind the universe's tape, would we see the same events play out, or does chaos ensure every iteration would be unique? Could a theory of everything derived from cosmic maps reveal whether time itself has a direction, or if the arrow of time is just an emergent property of the universe's structure? And what would it mean for free will if the universe's fate is as predictable as the orbit of a planet? The most tantalizing possibility is that cosmic cartography might one day reveal not just our universe's destiny, but whether others exist beyond it. If anomalies in the web like filaments bending oddly or voids too large to explain trace back to collisions with other universes in the distant past, mapping those scars could open a window into the multiverse. It's a dizzying thought. The same tools we use to navigate galaxies might eventually let us glimpse realities where the laws of physics are unrecognizable. For now, these ideas lie at the edge of science and speculation. But every new survey, every deeper map, brings us closer to answering whether the universe's story is written in stone, or if, like any great epic, its ending remains unwritten, waiting to be discovered in the hidden folds of space and time. The universe's hidden highways might hold more than just galaxies and dark matter. They could be the ultimate transit system for civilizations far beyond our own. Imagine an advanced extraterrestrial society looking up at their night sky, not as a scattering of stars, but as a roadmap of cosmic filaments and gravitational currents, plotting routes between worlds like ancient sailors following ocean currents. This isn't just science fiction. Theoretical physics suggests that the very structures we've been mapping, wormholes threading through space-time, warp bubbles riding gravitational waves, could be nature's version of interstellar freeways waiting to be unlocked. Take wormholes, those hypothetical tunnels connecting distant points in space. While they've long been a staple of sci-fi, some physicists argue they could form naturally along the cosmic web's densest filaments, where space-time is already warped by immense gravitational forces. Picture a subway system burrowing beneath a city, except here, the tunnels are forged by the universe itself, with dark matter acting as the scaffolding that keeps them stable. The catch, traversing them would require technology to prevent collapse, perhaps by threading them with exotic matter, a substance with negative energy that could prop open the throat of the wormhole like cosmic scaffolding. It's a long shot, but if such pathways exist, they'd explain how a civilization could hop between galaxies without breaking the speed of light. Then there's the Alcubierre warp drive, another tantalizing concept. Instead of moving through space, this theoretical engine would compress space-time ahead of a ship and expand it behind, effectively surfing a wave of distorted geometry. Recent studies suggest that the energy required might be lower than once thought, especially if harnessed along cosmic filaments, where dark energies push and dark matters pull, could provide natural currents to ride. Think of it as catching a gravitational updraft, like a glider using thermal winds to stay aloft. If advanced beings have mastered spacetime's wrinkles, the cosmic web's filaments could serve as their intergalactic trade winds. But how would we even spot such travelers? SETI, the search for extraterrestrial intelligence, has traditionally listened for radio signals, but maybe we should also be scanning the cosmic web for anomalies. Unexplained energy fluctuations along filaments, or patterns of gamma-ray bursts that resemble navigation beacons, could hint at activity. Some astronomers propose looking for Fermi bubbles, vast structures of radiation that might form near a wormhole's mouth, like exhaust from a starship's engine. Others suggest monitoring gravitational waves for unnatural ripples, the space-time equivalent of wake left by a passing vessel. The most intriguing clue might come from vanishing stars. Over the past decade, surveys like the Vasco project have catalogued objects that mysteriously disappear from the sky. While most are likely mundane failed supernova or asteroids, a handful defy explanation. Could some be evidence of civilizations harnessing cosmic highways, their departures or arrivals briefly flickering into view? It's a wild idea, But in a universe as vast and ancient as ours, the possibility that someone else has already cracked interstellar travel isn't just plausible, it might be inevitable. Of course, skeptics argue that such speculations are premature. We've yet to confirm even simple extraterrestrial life, let alone galaxy-hopping engineers. But history shows that today's wildest theories often become tomorrow's textbooks. The cosmic web's filaments, once mere mathematical predictions, are now mapped in stunning detail. Who's to say what else our maps will reveal as we learn to read them more deeply? Whether these highways ever carry travelers or remain untouched by intelligence, one thing's certain: the universe has built the infrastructure. The only question is whether someone's out there using it. Step into a virtual universe where galaxies swirl at your fingertips, where you can plunge through the heart of a dark matter filament or drift across a billion light-year void with the tilt of your head. This isn't science fiction, it's the cutting edge of cosmic cartography, where virtual reality is transforming how we explore the universe's grand design. Scientists are now using VR headsets to navigate colossal datasets, turning abstract numbers and equations into immersive, interactive landscapes. Picture floating inside a 3D map of the Sloan Digital Sky Survey, where millions of galaxies glitter like fireflies, each one precisely placed based on its real-world coordinates. With a flick of your wrist, you can zoom from the local group to the farthest quasars, tracing the cosmic web's delicate threads as if they were ropes you could grasp. This tech isn't just for astronomers, it's democratizing space exploration. Projects like the Virtual Universe project at MIT let anyone strap on a headset and tour the cosmos, no PhD required. Suddenly, concepts like redshift and gravitational lensing aren't just equations in a textbook, they're visceral experiences. Feel the tug of a black hole's gravity well as you orbit it, or watch light bend around an invisible dark matter clump like water flowing around a rock. Even school kids can now witness the large-scale structure of the universe unfold over billions of years, compressed into minutes, a time lapse of cosmic evolution playing out in their living rooms. But VR's real power lies in revealing hidden patterns. Astronomers at the University of California, Santa Cruz, built a VR tool called Space-Time Explorer that lets researchers literally walk through their simulations, spotting irregularities in galaxy distributions that flat screens might miss. One team discovered a previously overlooked filament connecting two clusters by noticing its subtle curvature, something that only became obvious when they could examine it from all angles. It's like the difference between studying a city map and hovering above the actual streets in a helicopter. Context changes everything. The future is even wilder. Imagine collaborative VR spaces where scientists across the globe meet as avatars inside a shared cosmic simulation, tweaking dark energy parameters in real time to see how the web responds. Or public exhibits where visitors don haptic gloves to feel the gravitational pull of a supercluster. Some prototypes already integrate AI guides that explain what you're seeing, tailoring the experience to your curiosity, whether you're a casual stargazer or a grad student hunting for research topics. Yet for all its potential, VR cosmic cartography also exposes how much we still don't know. Gliding through these models, you'll encounter blank regions labeled unknown, not because the tech failed, but because our telescopes haven't peered there yet. These voids in the virtual map mirror the gaps in our understanding, a humbling reminder that every breakthrough reveals new frontiers. The universe's highways are waiting, and thanks to VR, we're no longer just reading the signs, we're finally riding the roads. Mapping the universe isn't just a scientific endeavor, it's an ethical minefield. As we chart galaxies and trace dark matter filaments, we're forced to confront questions that go beyond physics. Who has the right to claim cosmic knowledge? Should there be rules about how we explore or even alter the fabric of space itself? Consider the case of radio telescopes scanning the sky for signals. Those same instruments could one day detect whispers of extraterrestrial civilizations, raising the stakes dramatically. Do we have the right to broadcast our presence into the void without global consensus, potentially exposing Earth to unknown risks? Or does the urge to connect outweigh the caution? Then there's the issue of cosmic preservation. When we identify pristine regions of space like untouched gas clouds that could birth future stars, do we have an obligation to leave them undisturbed? On Earth, we've learned the hard way that unchecked exploitation leads to irreversible damage. The same principles might apply to the cosmos. Mining asteroids for rare minerals could fund space exploration, but it might also disrupt delicate orbital ecosystems or erase celestial bodies that hold clues to our solar system's history. Even something as seemingly harmless as satellite megaconstellations, like SpaceX's Starlink, already pollute our view of the night sky, complicating astronomy and dimming the stars for generations to come. Ownership adds another layer of complexity. Telescopes and satellites are often funded by nations or corporations, raising the question, is cosmic data a shared human heritage or can it be privatized? Companies selling high-resolution maps of the Moon or Mars for commercial ventures argue they're fueling innovation. Critics counter that turning celestial bodies into commodities risks repeating Earth's history of exploitation. And what if we discover something priceless like a habitable exoplanet? Would it fall under the jurisdiction of whoever's telescope spotted it first, or should it belong to no one or everyone? Perhaps the deepest ethical dilemma is existential. As we map the universe, we're also defining humanity's place within it. Are we passive observers, documenting the cosmos with reverence, or are we active shapers, destined to bend space-time to our will? The answer might lie in how we treat the universe's most fragile wonders, not as resources to plunder, but as part of a grand, interconnected system we're only beginning to understand. The maps we're making today don't just guide explorers, they'll define what kind of explorers we become. Every map we've ever drawn, from ancient star charts to glowing 3D models of dark matter, carries an unspoken question. What does it mean to plot our place in the infinite? Cosmic cartography does more than reveal the universe's structure. It holds up a mirror to humanity's deepest existential inquiries. When Edwin Hubble first proved galaxies were rushing away from us, he didn't just expand our understanding of space, he shattered the illusion that we occupy a central, privileged position in the cosmos. Suddenly, Earth wasn't just a pale blue dot. It was a speck adrift in an ocean of unfathomable scale, where entire galaxies vanish over the horizon like ships swallowed by fog. This humbling perspective forces us to confront an unsettling truth. The universe wasn't designed for our comprehension. The cosmic web's filaments stretch across billions of light years, indifferent to whether eyes ever evolved to witness them. Yet here we are, tiny and fleeting, trying to decode a story written in gravitational waves and redshift, a story that began long before us and will continue long after. There's a profound tension in this pursuit. On one hand, mapping the universe is an act of defiance against our own insignificance, a way to carve meaning from the void. On the other, it's a reminder that we're temporary guests in a cosmos that operates on timescales we can't fully grasp. Philosophers have wrestled with this duality for centuries. Immanuel Kant argued that space and time aren't external realities but frameworks of human perception, lenses through which we filter the universe's chaos into something navigable. Modern cosmic cartography tests this idea daily. When we map dark matter's invisible tendrils or simulate the universe's birth, are we uncovering objective truth, or are we projecting order onto a reality that transcends our mental categories? The very tools we use, mathematics, physics, even language, are human inventions. Could the cosmic web we see be just one possible interpretation of a deeper, stranger reality? Yet mapping the universe also reshapes what it means to be human. Knowing that the atoms in our bodies were forged in dying stars connects us to the cosmos in a visceral way. We're not just observers, but participants in an ancient, ongoing exchange of matter and energy. Indigenous cosmologies have long embraced this interconnectedness, with traditions like the Aboriginal songlines weaving land and sky into a single, living map. Modern science echoes this intuition when it reveals how galaxies exchange gas along filaments or how supernova explosions seed future star systems. The boundaries between us and the universe blur until they vanish entirely. Perhaps the most radical insight cosmic cartography offers is this: the act of mapping changes the mapper. Every time we push the boundaries of the known, whether by discovering a new supercluster or spotting an anomaly in the cosmic microwave background, we're forced to reconsider our assumptions about existence itself. Are we alone? Is the universe finite or infinite? These aren't just scientific questions, they're existential ones, and the answers or lack thereof ripple through culture, religion, and art. The Hubble Deep Field image, revealing thousands of galaxies in a patch of sky no larger than a grain of sand held at arm's length, didn't just advance astronomy, it redefined how an entire generation imagined their place in the cosmos. In the end, cosmic cartography is as much about inner space as outer space. The farther we chart the universe's highways, the more we're compelled to map the uncharted territories within the awe, the terror, the wonder that comes from staring into the abyss and realizing the abyss is staring back. The great cosmic maps we build aren't just guides to the stars, they're mirrors reflecting our boundless curiosity, our hunger for meaning, and our stubborn refusal to let the vastness silence our questions. And in that refusal, we find something extraordinary, not centrality, but connection, a thread woven through the cosmic web, tying us to everything that was, is, and ever will be. You might think mapping the universe requires a doctorate and access to billion-dollar telescopes, but some of the most groundbreaking discoveries in cosmic cartography have come from everyday people sitting at their kitchen tables. Take Galaxy Zoo, a project that turned astronomy upside down by inviting the public to classify galaxies from telescope images. What started as a simple online experiment in 2007 became a revolution, with volunteers, teachers, artists, retirees spotting celestial oddities that algorithms missed and professionals overlooked. One participant, a Dutch schoolteacher named Hanny van Arkel, discovered an entirely new class of object now called Hanny's voorwerp, a glowing green cosmic ghost lit by the radiation of a long-dead quasar. Her find, along with thousands of other citizen contributions, proved something radical. The human brain's knack for pattern recognition, even untrained, could outperform supercomputers when it came to picking out cosmic quirks. The secret sauce, crowdsourcing, taps into something machines still struggle with: intuitive leaps. While computers excel at measuring a galaxy's size or redshift, they often stumble when confronted with the unexpected. A warped spiral arm hinting at a past collision, or an unusual dust lane suggesting gravitational turmoil. That's where human eyes shine. In one famous case, Galaxy Zoo volunteers flagged a peculiar galaxy labeled UGC 1281, which turned out to be a rare polar ring galaxy, a cosmic bull's-eye where stars orbit perpendicular to the main disk, likely the aftermath of a galactic train wreck billions of years ago. Professional astronomers had scanned the same data for years without noticing, but classifying galaxies is just the start. Projects like Backyard Worlds scour infrared surveys for brown dwarfs, failed stars lurking in our cosmic backyard, while Einstein at Home lets volunteers donate idle computer time to sift through gravitational wave data for pulsar signals. The most ambitious might be the Dark Energy Explorers project, where anyone can help trace cosmic web filaments by marking galaxy clusters in deep field images. These efforts aren't just busy work, they're filling gaps in maps that even AI struggles to navigate. When the Vera C. Rubin Observatory comes online, its avalanche of data will make citizen science more vital than ever. There simply aren't enough professional astronomers to analyze the tens of billions of objects it will detect. What's truly beautiful is how these projects democratize discovery. A retired mechanic in Brazil might spot a supernova before automated alerts do. A high school student in Norway could cross-reference galaxy motions to reveal a hidden filament. And sometimes the tools are as simple as a backyard telescope. Amateur astronomers regularly track variable stars, contributing light curves that help measure cosmic distances, or monitor active galactic nuclei for flares signaling black hole meals. Their observations, logged in databases like the American Association of Variable Star Observers, become part of the global toolkit for mapping the universe's structure. This collaborative spirit is rewriting what it means to explore. Gone are the days when astronomy happened only atop remote mountaintops. Now, the Cosmic Cartographer's Toolkit includes a smartphone app that lets you tag galaxy mergers during your morning commute, or a browser extension that turns idle scrolling into quasar hunting. The universe's highways are too vast for any one group to map alone, but together, we're charting frontiers no single mind could conquer. The human brain evolved to navigate forests and savannas, not to comprehend filaments of galaxies stretching 1 billion light-years. Try picturing that distance for a moment. A single light-year is already an absurd 6 trillion miles, a scale where numbers lose meaning. Now multiply that by 1 billion. Our neural wiring simply wasn't built for this. We're like ants trying to grasp the internet, our mental tools hopelessly outmatched by the cosmos's grandeur. This perceptual gap isn't just a curiosity, it's the Everest of science communication. How do you translate structures so vast they defy intuition into something a sixth grader or a curious adult can understand? Enter the Cosmic Cartographer's bag of tricks. To shrink the universe down to human scale, they often turn to analogy. Imagine the cosmic web as a city subway system, where major galaxy clusters are central hubs like Grand Central Station, and thinner filaments are local train lines feeding into them. Dark matter becomes the unseen tunnels dug beneath the streets, guiding the flow of celestial traffic. These metaphors work because they anchor the alien to the familiar, even if they're imperfect. The trade-off, like translating poetry, some nuance gets lost but the essence survives. Some scientists ditch analogies altogether for interactive scaling. Websites like Scale of the Universe let you scroll from a coffee bean to a supercluster, each click expanding or shrinking your view by powers of 10. The genius lies in the pacing. Zooming out gradually lets your brain recalibrate, like stepping back from a painting until individual brushstrokes resolve into a coherent image. Virtual reality takes this further, placing users inside galaxy collisions or at the edge of observable space, leveraging our spatial awareness in ways flat screens can't. Yet even these tools hit walls when confronting cosmic time. A video compressing the universe's 13.8 billion-year history into 10 minutes might show galaxies forming like blooming flowers, but it risks implying everything happened in a tidy sequence rather than an overlapping chaos. To counter this, astronomers sometimes use time crystals, 3D printed models where each layer represents an epoch. letting you physically hold deep time in your hands. Others map cosmic evolution onto a single Earth year, with the Big Bang at midnight January 1st and modern day at the next year's stroke of midnight. Suddenly, human history occupies just the last cosmic second before the ball drops, a visceral reminder of our fleeting presence. The most inventive solutions come from art-science collaborations. Data sonification turns galaxy motions into musical notes, where higher densities play as chords and voids as silence. One project mapped the cosmic web's structure onto a labyrinth of vibrating strings. Plucking them made dark matter's gravitational pull audible as harmonic resonance. These approaches exploit our brain's uncanny ability to detect patterns in sound and texture when vision fails. Ultimately, every visualization is a compromise between accuracy and accessibility. A perfect map of the universe would be as incomprehensible as the cosmos itself, an infinite, multi-dimensional tangle of warping space-time. The best cosmic cartographers don't just simplify, they curate, choosing which mind-bending truths to highlight and which to temporarily set aside. Their work isn't about shrinking the universe to fit our minds, but expanding our minds to glimpse the universe. And in that expansion lies something extraordinary, the chance, however fleeting, to stand at the edge of the knowable and stare into the abyss without turning away. It seems counterintuitive at first. How could studying galaxies billions of light years away possibly help us predict tomorrow's weather or track rising global temperatures? Yet the threads connecting cosmic cartography and climate science are stronger than you might think. Both fields grapple with deciphering patterns in overwhelming oceans of data, whether it's the faint glow of distant galaxy clusters or the chaotic swirl of atmospheric currents. The same mathematical tools developed to map the universe's invisible scaffolding are now quietly revolutionizing how we understand Earth's changing climate. Take machine learning algorithms trained to spot dark matter's ghostly fingerprints. These programs excel at finding subtle correlations in massive datasets, teasing out hidden structures from noise. Climate scientists have adapted these very algorithms to analyze satellite images of cloud formations, identifying patterns that hint at developing storms or shifting jet streams. It's like using a telescope designed for deep space to suddenly focus on Earth. The lens stays the same, but the view transforms entirely. Projects like the European Space Agency's Climate Change Initiative even repurpose galaxy classifying AI to track melting ice shelves, treating glacial crevices like cosmic filaments waiting to be mapped. The parallels run deeper than software. Both cosmic and terrestrial cartographers face the challenge of incomplete data. Gaps in telescope coverage mimic the blind spots between weather stations. To fill these voids, cosmologists developed interpolation techniques that climate modelers now use to predict temperatures in unmonitored regions, whether it's the middle of the Pacific or the peaks of the Himalayas. Even the way dark matter simulations account for gravitational uncertainties has inspired new methods to quantify the margin of error in climate projections, helping policymakers understand which forecasts are rock solid and which hinge on finer variables. Perhaps the most striking overlap lies in visualization. The 3D modeling tools that bring the cosmic web to life, spinning it into glowing tendrils and voids, also render atmospheric CO2 concentrations as swirling, color-coded plumes. NASA Goddard Institute regularly collaborates with astrophysicists to borrow their data visualization tricks, turning abstract climate metrics into immersive experiences. Suddenly, a century of rising sea levels isn't just a graph, it's a time-lapse of virtual coastlines dissolving under digital tides, rendered with the same cinematic flair as a galaxy collision. This cross-pollination goes both ways. Climate scientists' work on ocean currents has refined models of plasma flows in galaxy clusters, while atmospheric turbulence studies help explain how gas moves along cosmic filaments. The most profound lesson might be philosophical. Whether mapping Earth or the cosmos, we're learning that everything is interconnected. A dark matter filament guiding galaxies and a jet stream steering storms both obey the same universal laws, just operating on scales that stretch the limits of human imagination. So the next time you check a weather app or see a headline about climate projections, remember somewhere in those algorithms are echoes of the quest to map the universe. And when astronomers trace the cosmic web's next filament, they might be borrowing techniques born from the urgent need to understand our own fragile planet. In the grand tapestry of science, the threads between stars and storms are woven tighter than we ever knew. The universe's hidden highways don't arrive on our screens as cold datasets or endless columns of numbers. They burst forth in swirls of gold, crimson, and sapphire, transforming the cosmos into a gallery of celestial masterpieces. Cosmic cartography is as much an art as it is a science, where the brushstrokes are gravitational lensing arcs and the palette is the electromagnetic spectrum. Take the Dark Energy Survey's map of the southern sky, a tapestry of 300 million galaxies rendered in gradients of indigo and violet, each dot a distant island of stars. Or the Planck satellite's all-sky image of the cosmic microwave background, its mottled blues and yellows revealing the infant universe's temperature variations like brush marks on a cosmic canvas. These aren't just pretty pictures, they're translation devices, turning the language of physics into something our eyes and hearts can grasp. Behind every visualization lies a series of deliberate choices. When mapping dark matter's invisible tendrils, artists and scientists collaborate to assign colors to gravitational pull, warmer hues for dense knots where galaxies cluster, cooler tones for the sparse voids between. The famous Millennium Simulation movie, which traces the universe's evolution over 13 billion years, uses this technique to breathtaking effect. Gas filaments glow emerald as they feed growing galaxies, while merging clusters explode in fireworks of magenta and gold. It's a reminder that without these artistic interpretations, the sheer scale and complexity of cosmic structures would remain locked away in supercomputer outputs, inaccessible to all but a handful of specialists. Some of the most striking maps emerge from combining wavelengths invisible to human eyes. The Chandra X-ray Observatory's images of galaxy clusters overlay deep blues for high-energy X-rays onto Hubble's visible light golds, revealing superheated gas swirling around black holes like cosmic auroras. Meanwhile, radio telescopes like ALMA paint molecular clouds in fiery oranges, exposing stellar nurseries hidden within cosmic dust. These composite images aren't artistic license, they're layered truths, each wavelength a different verse in the universe's multisensory poem. The artistry extends to how these maps engage time. Interactive tools like the Cosmic Web Explorer let users fly through filaments in 3D, adjusting transparency to peer through galaxy walls or pausing to study a cluster collision mid-dance. Others, like the Sloan Digital Sky Surveys, fly through video, compress millions of light years into minutes, giving viewers godlike perspective on the universe's architecture. These experiences borrow from video game design and cinematic storytelling, proving that to map the cosmos compellingly, you need both a physicist's rigor and a filmmaker's flair. Perhaps no map better blends beauty and revelation than the Laniakea supercluster visualization. In 2014, astronomers redefined our galactic neighborhood by tracing the flow of galaxies toward the Great Attractor, revealing a structure 500 million light-years wide. The team worked with data artists to render this colossal network as a river of gold streaming through space, with the Milky Way a mere speck bobbing along one tributary. The result wasn't just scientifically groundbreaking, it was sublime, making the abstract concept of a supercluster feel tangible for the first time. These cosmic cartographers are modern-day explorers in the tradition of Humboldt and Mercator, but instead of sketching coastlines, they plot gravitational wells and Baryon acoustic oscillations. Their maps do more than guide research, they redefine how humanity sees its place in the cosmos. When you gaze at one of these radiant visualizations, you're not just looking at data. You're witnessing the universe revealing itself, one breathtaking brushstroke at a time. The cosmic web we've mapped so far is like a single page torn from an infinite book. We've barely begun to read the story. For all our towering achievements in cosmic cartography, the deepest mysteries still loom larger than superclusters. Take the most fundamental question: what lies beyond the observable universe? Our telescopes can only see so far, about 46 billion light-years in any direction, before hitting the cosmic horizon where light hasn't had time to reach us since the Big Bang. But here's the mind-bending part. Most cosmologists agree this visible universe is likely just a speck within something far vaster. Imagine standing in a foggy forest where you can only see a few feet in any direction. You'd never guess the true scale of the wilderness beyond. Current theories suggest the full universe could be at least 250 times larger than what we observe, or possibly infinite. Some models even propose an eternal inflation scenario where new universes constantly bubble into existence like foam in an endless ocean. Then there's the enigma of cosmic dimensions. The filaments and voids we chart might be mere shadows of higher dimensional structures we can't perceive. String theory predicts up to 10 spatial dimensions curled into sizes smaller than atoms, but what if some are stretched across cosmic scales? Certain anomalies in the cosmic web, like filaments that appear improbably aligned over billions of light-years, have sparked wild speculation. Could these be echoes of gravitational forces leaking from adjacent dimensions, like ripples crossing between parallel ponds? The most tantalizing clue comes from the cosmic microwave background's so-called axis of evil, a peculiar alignment of temperature fluctuations that some theorists argue could hint at a pre-Big Bang geometry imprinting itself on our dimension. Dark flow presents another puzzle. Galaxy clusters aren't just drifting apart with the universe's expansion. Many are streaming in the same direction at baffling speeds, as if tugged by something colossal beyond our horizon. Some propose this could be the gravitational pull of a supermassive structure, perhaps a concentration of matter so vast it dwarfs the Shapley supercluster. Others suggest more radical explanations, that we're feeling the tidal forces of a neighboring universe brushing against ours in the multiverse foam. Perhaps the most haunting mystery is the great cold spot in the cosmic microwave background, a region hundreds of millions of light-years wide that's inexplicably cooler than its surroundings. Is it a scar from a collision with another universe, a titanic void where dark energy's grip is stronger, or something even stranger, like a defect in the very fabric of space-time left over from the universe's birth? These aren't just academic riddles, they're cracks in our understanding where future breakthroughs may pour through. Every unexplained warp in the cosmic web, every anomalous motion of galaxies, could be a clue pointing toward physics beyond Einstein, beyond quantum theory, beyond anything we've dared imagine. The greatest maps aren't those that fill in all the blanks, but those that show us where the uncharted territories begin. And in cosmic cartography, those blank spaces still dwarf everything we've mapped. As we stand at the edge of the known universe, gazing at the intricate web of cosmic highways we've painstakingly charted, it's humbling to realize how much remains hidden in the shadows. Every filament of dark matter, every sprawling supercluster, every enigmatic void we've mapped isn't just a scientific milestone. It's a waypoint in humanity's grand journey to understand where we come from and where we're headed. The cosmic web isn't just out there, it's part of us. The atoms in our bodies were forged in the hearts of stars that once rode these same gravitational currents, their ashes now woven into our very being. Think about the tools we've built to uncover these secrets: telescopes that peer back in time, algorithms that decode the whispers of dark energy, simulations that recreate the universe's birth. Each one is a testament to human curiosity, to our refusal to accept the darkness as empty. And yet, for every question answered, a dozen new mysteries emerge. Why do some filaments defy gravity's predictions? What lurks in the voids between galaxies? Could the cosmic web be threaded with dimensions beyond our perception? The map we've drawn is still rough, its edges fading into uncertainty, but that's what makes the pursuit so thrilling. This isn't just about science, it's about storytelling. For millennia, humans have looked to the stars and seen gods, animals, and heroes. Now we see filaments and nodes, but the wonder remains the same. The difference is that today, we're not just imagining, we're decoding. Every new survey, every breakthrough, adds another layer to the greatest story ever told. The epic of how a universe of chaos gave rise to galaxies, planets, and life capable of contemplating its own origins. So what's next? Perhaps one day we'll find evidence of other cosmic webs beyond our own, or uncover the true nature of dark energy. Maybe we'll even detect signs that the universe's highways have been traveled by others. Whatever lies ahead, one thing's certain: the cosmos will keep surprising us, and that's why we keep exploring, not just to fill in the blanks on a map, but to remind ourselves that the universe is stranger, grander, and more interconnected than we ever dared to dream. If this journey through the cosmic web has sparked your curiosity, you're already part of the adventure. Share your thoughts below. What cosmic mystery fascinates you most? And don't forget to subscribe so you won't miss our next voyage into the unknown. Until then, remember, the universe isn't just something we observe. It's a story we're all helping to write, one discovery at a time.